Right, everybody. So now you should be able to see the PowerPoint presentation on the left side of the screen and the Blackboard on the right side. Anybody has a problem seeing those two sides of the screen? Anybody can hear me? All is good? All right, great. Sorry for the delay. I'm still doing this for the very first few times. I'm trying to enhance everything to look better, but I'm not a great expert in the field. All right, so if you remember last class, we did discuss few topics of the immunology. And if you remember, we did discuss two main components of the immune system. Those were the innate immunity and the adaptive immunity. If you remember, innate immunity, this consists of the first lines of defense. Those were our surface barriers. This includes the skin and the mucous membranes, and they play a very important role in limiting the invasion of the pathogens inside the internal tissues. So we also did discuss few of the other parts of the innate immunity. And if you remember, this did include the internal defenses, which were the cells, chemicals, and we've got two processes. We discussed only one of them, which was the inflammation, and we still have one to discuss today, which is the fever. So for the innate immune cells, we did divide them into two major categories. Those were the phagocytes and the natural killer cells. If you remember, phagocytes are like my macrophages and my neutrophils. And the natural killer cells, those are a type of lymphocytes that still are part of the innate immunity. What I mean again by innate immunity, I am non-specific type of immunity. I'm not targeting any specific pathogen. I am acting on any non-self antigen. I'm targeting any kind of pathogens that is not presenting self antigens. So we did also discuss two of the very important chemicals that we share as part of our innate immunity. Those were the interferons, and if you remember, interferons, those were the SOSs that will be sent from the viral infected cells. Remember, if I have a cell that is virally infected, like this one, for example, on here, I'm infected by a virus, and the virus that will be allowing its genetic material to pass to the inside, where it's gonna be able to get integrated within the host cell genome. So within the DNA of the host cell, the viral genome will be integrated, and this will allow it to use everything from the host cell to build up copies of itself. And those viruses, those copies of the virus, will be released from the cell to infect neighboring cells. So to interfere with the progression here of the infection, we've got some genes that will be turned on the infected cells. And those genes are coding for special proteins that we've called the interferons, and those interferons are going to be released to the outside of the infected cell as warning messages to the neighbor cells. If you remember, neighbor cells should have surface receptors for them to receive this message. And as they receive the message, this will send internal signals that will stimulate specific genes on the neighbor cell to become activated. And this gene now is going to be producing antiviral proteins that will be blocking the replication of the virus. So the virus here, when it tries to inject its genetic material and to integrate its genetic material with the DNA, it gets blocked by those protein particles that would be formed by the neighbor cells, the non-infected cells. And this takes place by being stimulated by those chemicals released from the infected cells. Those are what we call the interferons. We also did discuss another type of innate immunity, which was the chemicals normally located within your bloodstream. Those are around 20 different types of plasma proteins, normally circulating freely in your bloodstream as plasma proteins. So whenever you get exposed to an infection, so this is my bacteria, let's say, and this bacteria is causing harm to my body. Other cells in the immune system, as we're going to learn today, will be responsible to produce immunoglobulins that will be attached to this bacterial cell, marking it for destruction. But actually, the antibodies here will be playing a very limited role in killing or getting rid of the virus. They are just enhancing the destruction of the bacteria. So we see on here, in order for me to destroy this bacteria, I need to recognize it first as non-self. And again, I recognize that this is non-self because other cells in the immune system will be producing antibodies that will bind to it. Once I've got the antigen-antibody complex here, this means I am ready to go. I have antigen attached to antibodies, so those antigens are not mine, so I need to destroy this marked cell. So in order for me to destroy the marked cell, those plasma proteins that we call the complement will be forming pores within the cell membrane of the bacteria. And those pores will be causing the cell lysis. How those pores will cause the cell lysis? Because simply now the bacterial cell is not able to regulate what is passing to the inside and what is leaving to the outside of the cell. So I have no control on my metabolic activities. I have no control on anything. So the cell gets destroyed. All right, this is the other chemicals that shared in our innate immunity. Again, the main stimulus for the activation of those plasma proteins is the presence of antigen attached to an antibody. Once you've got antigen-antibody complex on here, this will allow you to attack the cell, forming those pores within its cell membrane. We discussed also last class an innate immune response, which was inflammation. If you remember, if I've got a bacterial cell, or cells of mine which are virally infected. So I have infection on the inside. Those would be causing the formation of chemicals. many chemicals, and those chemicals will be causing inflammation, and we call those chemicals, those are my inflammatory mediators. Like what inflammatory mediators? Like, for example, the complement that we've just discussed. So once I have activated complement, this tells me that there is something wrong, there is an infection, I need to allow inflammation to take place. Like histamine, like cytokines, kinines, prostaglandins, leukotrienes, all those are chemicals that would be released by different means from immune cells. This will tell the body that there is something going wrong. So how your body responds to this attack, it's gonna be trying to recruit as many immune cells as it can. And how will it do this? By dilating the arterioles, dilating the blood vessels. And when I dilate the arterioles, dilating the vessels, I get more cells delivered to the site of the infection. It's like calling your friends if you have a fight. So if you remember, we did mention few cardinal signs for inflammation. Those were, if I'm describing my joint, which is inflamed, my eye, my skin, what are the cardinal signs of inflammation? If you remember, it's going to be red, it's going to be hot, it's going to be tender, painful, and it's going to be swollen. What causes all this? Again, inflammation in two words is going to be blood vessels dilation. So you dilate the blood vessels, you dilate the arteries, and as you dilate the arteries, what's going to happen? Remember, this increases my hydrostatic pressure within the capillaries. Remember, those arterioles are getting the blood delivered to smaller vessels, which we've called the capillaries. And those capillaries will allow the fluid to travel between the cells. What is the driving force for the fluid here to leave the capillaries and to travel between the cells is the hydrostatic pressure they gain from the arterioles. So if I'm increasing the hydrostatic pressure by dilating the vessels, this allows more fluid to travel. And as more fluid travels outside of the blood vessel of the capillaries, and few of it returns back before it gets drained into the venules. So this is gonna cause the accumulation of the fluid between the cells. This what will cause the swelling, accompanying the inflammation. More blood gets delivered to the site of inflammation. This what will make the inflamed site red, carrying the internal body temperature to the outside, to the site where I have the inflammation. This will make the inflamed site hot. And remember, between your tissue cells, you've got those nerve endings that are detecting multiple sensations. And if I'm accumulating fluids, this is gonna cause compression of those terminal ends of the nerve fibers. And as I compress them, this will cause pain on touch. I have tenderness here of the inflamed site. Remember, is inflammation something good or bad? Remember, this was both good and bad. How is it both good and bad? If I have exaggerated inflammation, excessive dilation of the blood vessels, remember, this is gonna cause a major problem. If all arterioles are gonna be dilated, this will be reducing my resistance. And if you remember, if I have a reduction in my arteriolar resistance or my peripheral resistance, this will cause a drop in my blood pressure and so my tissue perfusion. And a drop in the tissue perfusion is what we've called, if you remember, this is shock, anaphylactic shock. Anaphylactic shock is caused by what? It's caused by hypersensitivity to a specific antigen. This will cause a exaggerated inflammatory response. A lot of inflammatory mediators going to be released all at the same time, dilating a huge number of arterioles. This will reduce the resistance, causing the shock. Why is it good? If you remember, first things that we've mentioned, why inflammation is good. Remember, it's going to be preventing here the spread of the infection. I am surrounding the pathogen from everywhere, so it doesn't have anywhere to escape. I'm accumulating the fluid. I'm reducing the amount of fluid returning back from my tissues. Remember, I'm reducing the amount of fluid getting back to the getting back from my tissues to the blood. So this reduces the risk of disseminating the infection. Another thing that I will be disposing here, I will be disposing the cell debris that are resulting from the destruction of my cells due to the infection and the pathogen cells. So I need to clean all the dead cells, whether mine or of the pathogen. So getting a lot of fluid to wash out those cell debris. Also, I'm setting the stage for repair and healing for this injured tissue. Remember, in order for me to rebuild my tissue, I need extra cells, extra oxygen, extra everything for the cells to proliferate back and to build up the damaged tissue. So I need extra everything to be delivered to the injured site. And this is going to be allowed by dilating the arterioles. And remember, dilation here of the arterioles is going to be my inflammation. All right. Any problems so far of what we've discussed last time? Any problem? Good so far? Any questions? All right. So we're looking here at a new, again, innate immune response, which is fever. What causes fever is here the presence of a pathogen. So I've got this bacteria on here. It carries antigens which are not mine. So my immune system recognizes this bacteria by detecting those non-self antigens presented on its outer surface. So it starts to release chemicals to induce inflammation, like what we've mentioned, to induce fever as well. And the chemicals that will be released from the immune cells when they get in contact with microorganisms or pathogenic cells, those are what we call the pyrogens. Those are the chemicals released from the immune cells that will result in fever. How the pyrogens gonna be causing the fever? So remember, we did have multiple levels of responsibility in the brain. Remember, we did have the level where you're gonna be taking very important decisions, your conscious mind, the voluntary motor activity, your perception, all this is gonna be taking place in the cerebral cortex or the cerebrum. And remember, we did need this was considered like the president here of this organization. And underneath it, the one who will be organizing, editing, sorting what should be traveling to your conscious mind, what should be traveling to the president here is going to be the vice president. And remember, the vice president in the brain here, this was the thalamus. Thalamus here is the one that source edits the information before it reaches the president or the cortex, cerebral cortex. So I need another level this time, and this time the other level here is going to be responsible for the very basic automatic activities that will be taking place in your body. So you don't have to worry about regulating your heart rate, about regulating your body temperature, regulating the food and water intake, regulate, for example, emotions. So all this is going to be taking place in part lower than the thalamus. This is what we've called the hypothalamus. We've seen the hypothalamus many times this semester. We've seen it in the regulation of the blood pressure. We've seen it in the regulation of the water intake. We've seen it releasing the ADH. So hypothalamus is going to be responsible for many important functions that will allow you to survive, but still those functions are of an autonomic type. So one of the functions here of the hypothalamus is to regulate your body temperature. In your brain, in the hypothalamus, you have nerve cells that will act as a thermostat of the body. So what if I am detecting normal temperature, normal body temperature? Should I do anything? Yes, Azim, it's like the main regulator of all autonomic activities. Main regulator of all autonomic activities. I shouldn't worry about making decisions about heart rate, body temperature, food intake. So my question here, if I have a normal body temperature, should I have to do anything? No, I won't be doing anything. So I won't be sending out any signals. But your temperature, like anything in your body, is going to be dynamic. It's not static. It's not stable. It's not going to be, it's going to remain forever the same. So here, whenever I have a drop in my body temperature, it's too cold outside, let's say, what will I do? The hypothalamus sends out signals to your skeletal muscles, and your skeletal muscles will start to contract. I will send out signals to the blood vessels in the skin. This is my skin on here. For them to constrict, reducing the amount of blood delivered to the skin, so I won't be losing my body heat to the outside by radiation. So I'm not trying to lose the heat outside, I'm trying to contract the skeletal muscles. And as I contract the skeletal muscles, remember, a very big part of the energy consumed by the muscle contraction is going to be transformed into heat. 60% of the ATPs that you consume by your muscles is going to be transformed into heat. Only 40% is going to be transformed into a mechanical movement. So if we're looking on here, I'm sending out the signals to the skeletal muscles for me to shiver. Contraction, contraction, contraction releases heat. In the same time, I'm limiting my loss by constricting the blood vessels in the skin. So this is how I would respond if I did have a reduction, if my body temperature goes down. What if my body temperature goes up, increased? If I have an increase in the body temperature, I will do what? I will be sending out signals, this time not to constrict the blood vessels of the skin, but to dilate the blood vessels in the skin. And as I dilate the blood vessels in the skin, this will get more blood delivered to my sweat glands, which will be filtering more fluid from the blood to be released out in the sweat. So I did here two things. I am increasing the amount of blood reaching my skin, so I have a better chance of losing part of the body heat out by radiation. Another thing that I've released water here is that would be cooling down my body temperature. So this water that's going to be cooling down the body temperature is going to be an extract from the blood. All right, so this is how I respond normally if I have an increase, and I will always have an increase in the body temperature from time to time. I will always have a reduction in the body temperature from time to time. Here, I'm trying to keep it balanced. Whenever it increases, I reduce it. Whenever I have a low body temperature, I try to increase it back to low. All right, so this is simply how I normally function as a hypothalamus. But what if, let's say this is my normal body temperature, 37 degrees Celsius. This is a normal body temperature on here. What if I did go to the hypothalamus and I did change the set temperature? I reset it to 42. So having a body temperature of 41, is it high or low? What do you think? It's high, right? It's high. And would I respond? What do you think? Would you respond in this case? So again, what is the set point? What is the set point in the thermostat in the hypothalamus? Now, the temperature in the thermostat is set at 42. So think of the AC. So we are together in the same room. Any suggestion? What is the best temperature for you for the AC? What is a good temperature that you set the AC on? 75? All right, 75. So you normally put the thermostat at 75. All right, but I feel cold at 75. I don't like 75. So what will I do? I will go to the AC, to the thermostat, and I will reset it to 78. What normally the AC is doing, so when you reach this temperature, it stops. It's not cooling down. All right, so now for you, 78 is high or low? 78 for you is high. Would the AC reduce it if I did reset it to 78? If I resetted the thermostat of the AC at 78, will it work? Will it cool down to your comfort? So the temperatures that you're comfortable at. Will it cool down to 75? No, because simply I did reset it to 78. So this is the same concept. This is what exactly happens in your hypothalamus. So I've got a pathogen that got recognized by immune cells. Once I recognize that this is a pathogen by detecting the surface antigens and stuff like this, and will start to release the chemicals. And remember, the chemicals here that will induce the fever are called my pyrogens. Those pyrogens will do what? Will reset the thermostat. So rather than hypothalamus acting at 37 to reduce your temperature, they won't send the signals out to the sweat glands until you reach 42. So if you are 41, would you be sweating to reduce the body temperature down? You won't be sweating. So your body temperature is gonna still remain high. So we're looking here, I didn't do anything at the effector organs, at the organs I'm affecting here. I did act on the thermostat. I did change the temperature. I did reset it. So rather than sending out the signals at 37 for you to reduce the temperature when it goes up, you won't send the signals out to the sweat glands until you get to 42. All right. So this is how I do induce fever in response to the infection. Any problem here? Any problem on how the fever gets induced? So your hypothalamus raises the overall normal body temperature when you're ill. Yes, exactly. So I did reset it. I won't respond. I won't interfere. So normally you are generating heat from the metabolic as a normal thing through your metabolic activity. So you're not interfering with this increase in the temperature because simply you did tell the hypothalamus, now you shouldn't act until you get to 43, 44. So if you are 41, it won't interfere. It won't send out the signal. So when I am sick, why would I be sweating? I feel that when I have fever, I will be sweating. Actually, sweating when you are sick, it simply means you are about to get rid of the infection. It's a good sign. Why? Because your immune system was capable now to reduce the viral load, to reduce the number of bacterial cells. So now it doesn't produce much pyrogens. So the hypothalamus is gonna be going back to its normal set point. So now it's gonna be detecting, now I have a high temperature, so I need to send out my signals to the sweat glands for me to sweat and reduce the temperature back to normal. But this is a good sign. Having sweating, this is usually taking place towards the end of the course of being ill. Joseph here, the pyrogens makes the temperature jump really high, or does it raise the minimal to start sweating? It raises the set point in the hypothalamus. So rather than responding, rather than hypothalamus sending out the signals rather than the AC start to cool down the room at 75, it won't start cooling the room until you get to 78. So at 77, it's high for me. It's a high temperature. I don't like it. It's the same concept. The hypothalamus will not be sending out the signals until you get to 42. So it's too high for you. So if you are 41, your hypothalamus is not sending out the signals to your effector organs for you to respond. Is this good, Joseph? Right, Mary. This is why we feel inside heat before it's noticed in the skin body. Usually we don't feel, you only feel the heat through your skin. All right, it doesn't have to be hot. Skin doesn't have to be hot, but you feel the temperature because simply the temperature, the thermoreceptors are located in the skin. All right, so you're gonna feel that there is an increase, and sometimes you won't even feel that you have fever. Somebody needs to check it for you, right? Because the receptors the receptors for detecting change in the body temperature, those thermoreceptors are located in your skin, not in your internal organ. Okay, Mary. All right, so Ariel, so the pyrogen's main job to reset the thermostat of the body. Yes, exactly. Exactly. For Victoria, what if the fever is too high? Will the hypothalamus regulate it? If it's too high, we should interfere before I reach this resetted new temperature in the hypothalamus. You should interfere here because simply this is going to have major complications, having a very high temperature or fever for a prolonged time. So this takes us here. All right, so why when you have fever, you feel cold? You feel cold simply because you didn't reach the 42. So you don't get a feeling yet that it's too high. So you see on here, for me, I am the one who did reset the thermostat when we were together in the same room. All right, so I set it at 78. So when it's 77, it's abnormal for you. It's high. It's above normal. Your normal is 75. It's high. But for me, it's still low. So I will feel that I am cold. All right, just get it closer a little. So this takes us to our question here. Is fever something good or bad? What do you think? Both. Why both? If it's good, it's good because first, having an increase in the temperature will do what all chemical reactions. If I am taking a chemistry class and I don't know much about chemistry, so what I will learn that temperature do what to the chemical reaction, speeds up the chemical reaction. And what chemical reactions do you need? You need all chemical reactions to be boosted. Like what? Like, for example, if I have cells, they need to release large number of immunoglobulins. And those immunoglobulins or antibodies are going to be proteins. So in order for me to form the proteins, I need to perform a lot of chemical reactions. So This is something that will speed up the production of immunoglobulins. I need the cells to duplicate the genetic material, to duplicate their organelles for them to divide and replicate, for them to be able to replace the injured cells. I need to speed up my metabolic activities, my chemical reactions, in order for me to, for example, build up collagen fibers by the fibroblasts to heal the injured site, and so on. So you're gonna be in need to boost up your metabolism. All metabolic reactions needs to speed up, and this is gonna be taking place if you have a higher temperature. Speeds up all those reactions. Another good thing for the fever is that it's gonna be sequestering the iron and zinc in the liver and spleen. Why is it important to move the iron and zinc here? From my blood vessels, and I keep them in the liver and the spleen, simply because many of the pathogenic cells gonna require them for their metabolic activity. So fever here is doing what? Imagine you have two arms. One is your immune cells. One is formed of immune cells, and the other one is formed of pathogens. So in order to get rid of the pathogen, what we're going to be trying to do, we're going to be increasing the number of immune cells, boosting up the metabolic activities, increasing the replication of those cells. And at the same time, you need to weaken your enemy. I need to reduce the rate of the proliferation of those bacterial cells, of the pathogen. So I'm doing both here. I am boosting up the metabolic reactions, speeding up the metabolism. At the same time, I am taking away important chemicals which are required for the pathogenic cells to proliferate. All right, so what do you take away from the bacteria inside the liver and spleen is going to be the iron and zinc. Why is it bad? It's bad if it was too high or it has been for a prolonged period. And prolonged period is going to be relative to the age, relative to the body size. All right. So what is going to be the problem here if I had fever, very high fever? The problem is that you have those proteins, those enzymes that you did boost the metabolism to build, and those will have specific shapes. And according to the shape of the protein, if you remember, you're going to have a specific action. So let's say this is an enzyme that looks like this at normal body temperature. If I did increase the temperature, it's like as if I am heating the egg white. So when you heat the egg white rather than being liquid and clear, it's going to be turning white and solid. So we call this is the denaturation of the protein. So rather than having this shape, I would be breaking down bonds, I would be deteriorating the molecule. So now I have lost my shape, which we're gonna call it the denaturation of the proteins. All right, so as a result, would I be able to function if I am, for example, carrying on the metabolic reaction that will be responsible for the production of ATP, for the production of energy? I won't. Okay? So what's going to happen? What's going to happen? All the chemical reactions that I was trying to boost will be slowing down. It will deteriorate major body functions, even can affect the brain, especially in children. That's why if a child has very high fever, you need to get it reduced as early as possible for it to not harm the brain. All right. So what do you think? Why is a moderate fever helpful in the immune response? Speeds up metabolism, causes liver and spleen to sequester the iron and zinc, slows the metabolism, both A and B, both B and C. All right, yes, exactly. As you've mentioned here, it's going to be both speeding up the metabolic reactions and sequestering the iron and zinc in the liver and spleen. All right, so moving on to the major part here of the immunity. So all what we've discussed so far are my innate immunity, parts of the innate immunity. Remember, we've got the surface barriers. This includes the skin. This includes my mucous membranes. This includes internal defenses like my cells, which includes the phagocytes. And if you remember, phagocytes are like the macrophages and neutrophils, natural killer cells. We've got in non-specific immune responses. This includes inflammation and fever. And we've got antimicrobial proteins. This includes two major ones that we've discussed. Those are my interferons and my complement proteins. All right, so all what we've discussed so far are part of my innate defenses. Moving on to the adaptive defenses, in which I'm relying on a special type of immune cells. Those are my lymphocytes. If you remember back from the previous chapter when we discussed the different types of white blood cells, we've discussed a type of white blood cells that we've called the lymphocytes. And I told you that when we discuss the immunity, you're gonna be able to figure out how important are those cells for your immune system. So if you remember, humoral, we did have two types of lymphocytes, and those were the B cells or the B lymphocytes and the T lymphocytes. We call the type of immunity mediated by the B lymphocytes. It's a humoral immunity. What I mean by humoral, it's mediated by the blood. So you release something in the blood takes care of the infection. Or this is what they thought when they were naming it. All right, so T lymphocytes, those are mediating a type of immunity that we call the cellular immunity. And the cellular immunity here is going to be mediated by, from its name, what do you think is going to be mediated by? Something that you won't be able to guess. It's going to be mediated by cells. Exactly. All right, so again, here I have blood, or to be more accurate, this is an antibody mediated response. Antibodies are the ones that will act in here, in this case. Cellular immunity, I have cells which are mediating the reaction. All right. Questions? All right, so let's have a look on here at the adaptive defenses. Adaptive defenses have very important common features. First, they are specific. They act specifically on target pathogens. So if I am a B cell that is attacking, let's say, rubella, I won't be attacking streptococcus. I am only going to be specifically attacking this pathogen because I am able to recognize the antigens on this specific pathogen. Not every single pathogen going to have those antigens. They are definitely different from one another, and each of them going to have different antigens presented on their outer surface. All right, so I have specificity. I have a specific I have a specific immune response. I have a systemic feature. What I mean by systemic, I will reach all the body organ systems. I'm acting on all different parts of the body. I can't reach anywhere because I will be acting by traveling through the blood. I can't reach everywhere. Either the B cells will be releasing the antibodies or the T cells, which will be acting on their own by traveling through the bloodstream. So I have a systemic response. And one of the most important features for the adaptive immunity is going to be that the adaptive immunity creates immunological memory. Memory here is a key that you're relying on when you are trying to get a vaccine created. So why do we get a vaccine, for example? For our immune cells to recognize this pathogen without getting exposed to the real pathogen. Why do you do this? Because simply, if I am recognizing the rubella, for example, why I don't just give part of the rubella like this? It's like a simulation to the real pathogen. This one here, the vaccine, is not going to cause harm. It's a dead cell or it's a weakened cell, so it doesn't cause harm. Would my cell recognize it? Yes, it's presenting the same antigen, same antigenic marker as a real pathogen. So I recognize it, I will have memory against it. So once I get exposed to it another time, I start to attack it at faster pace. So I don't have to get the infection during the time where the immune cells are still recognizing the pathogen. So if this is the first time I'm getting in contact with the pathogen, it takes me a while to start to have enough cells, to have enough immunoglobulins released, to have better knowledge of the pathogen for me to be able to get rid of it. So until I got this education, until I learn how to deal with the infection is spreading, it's causing harm. And as it causes harm, patient will be manifesting symptoms of the disease, might be lifelong complications. All right, so very important, very important feature here that we need to be aware of is that adaptive immune responses are going to be creating an immunological memory. Again, three features that we're looking at today for the adaptive immunity. First, the adaptive immunity is going to be specific, is going to be systemic, and it creates a memory. Again, two wings of the bird. Remember, two wings of my adaptive immune system. The bird on here has two wings. You can't fly with one wing. You are relying on both the adaptive in the adaptive immune system. You're relying on both the humoral immunity and the cellular immunity. Again, humoral immunity is going to be mediated by the B lymphocytes. This is my humoral immunity. For the cellular immunity, it's going to be mediated by the T lymphocytes. Yeah, so here we're talking, yes, what I was speaking of was the vaccine. I'm trying to simulate the infection. I'm trying to simulate the infection without giving the real pathogen to my patient. All right, so he creates a memory for him when he gets exposed to the real pathogen. He already recognized it before, so he's gonna act at a faster way, being able to get rid of the pathogen before it reaches the extent where it manifests and causes a disease. Now we're gonna get to the details of the vaccine and how they will work later in this chapter, maybe after break today. All right, so again, two main components of my adaptive immunity. Those are the cellular or the cell-mediated immunity and the humoral or the antibody-mediated immunity, which is mediated by the B lymphocytes. This one is going to be mediated by T lymphocytes. All right, so where do you get all your blood cells from? All the blood formed elements that we've discussed in the previous chapter, where all are coming from, they even come from the same cell, same stem cell. Can you, yeah, bone marrow. Bone marrow. Anybody remembers what cell is going to be responsible for the production of the blood formed elements? Yeah, bone marrow, to be more specific, it's red bone marrow. It's red bone marrow, but what was the name of the cell, the stem cell for all blood formed elements? Hepatocytes, this is the liver cell. Osteocytes, this is the bone cell. We're looking at hematocyte, you're close. Hemostasis means you stop bleeding. What is the first who will get it? First who will get it? Hemoblast, you're close. Hemoblast, close. Hemoblast. Hemocytoblasts. Here we go. Hemocytoblasts. All right, so hemocytoblasts were located where? Again, like what you said, in your bone marrow. So, but to be more specific, in the red bone marrow. So in the red bone marrow, I will be proliferating the hemocytoblasts to produce all blood fluid elements. This includes what? This includes my lymphocytes. Lymphocytes, neutrophils, monocytes, xenophils, basophils, all neutrophils, all white blood cells, red blood cells, megakaryocytes that will be producing the platelets. All of them are originating from my hemocytoblasts coming from the red bone marrow. So where do I get here my B and T lymphocytes? They are coming from my red bone marrow. This is where the hemocytoblasts are going to be kept. So they originate both from the red bone marrow. Both are originating from the red bone marrow. And what is the first major thing that happens in your life? A major event, first major event when you are around 5 years of age. Major decisions that your parents will be taking. They might be moving from one neighborhood to another neighborhood for you to do what? School, exactly. Schools. So you need to get education, right? One of the major changes that will be affecting each one of us is going to be school. It's going to be affecting the rest of your life. So where the B lymphocytes and the T lymphocytes are going to be going to school. For the B lymphocytes, they will remain in the same neighborhood. They won't be going anywhere. So they get their education in the bone marrow. So we call them the cells, the lymphocytes that remained in the bone marrow, B lymphocytes. Compared to the T lymphocytes, they will be getting their education outside of the bone marrow. They will travel to a gland located in the chest, which will be prominent at younger age. It's not prominent anymore because you have already activated most of those cells. All right, so see on here, they will be traveling to a gland located in the chest. On here, this is the thymus gland. That's why we're gonna call them thymus. Starts with T lymphocytes. So again, the very first major event that will be taking place for the lymphocytes after they originate from the bone marrow will be to get their education, to go to school. So for the B lymphocytes, they will complete their education in the bone marrow, homeschooled exactly, B lymphocytes. And for T lymphocytes, they will travel outside, they will change town maybe to get their education outside of the bone marrow, so they will be traveling to the thymus gland. So what do you need to learn in school as T and B lymphocyte? You need to learn to recognize and bind to one and only one specific antigen. One specific antigen. So for each B lymphocyte, I would be specifically recognizing one antigen, not any other antigen. Only one antigen. I'm able to recognize it. I'm able to get attached to it, to bind to it. All right? The first thing that those cells will need to learn. Another thing that those cells need to learn is to become self-tolerant. I need to create self-tolerance. What I mean by self-tolerance is simply to tolerate myself. What I mean by this, not attacking my own tissues, not destroying my own organs. So in order for you to not destroy your own organs and still recognize infections which are taking place inside your cells, in some cases like the viral, in a viral situation, you need to do two things to become self-tolerant. You need first to recognize the antigens on which you're going to be presenting, for example, a non-self antigen for those cells. So if I've got an infection on the inside, we'll be presenting the non-self antigens of the virus on a receptor. And those receptors on here are called the major histocompatible protein, or MHC. So I need first to recognize MHC, because this is where the non-self antigens is going to be presented along with some self antigens. So I need to be able to recognize this is mine. This is mine. I need to recognize it. But I don't need to recognize any other antigen presented on my cells. I need to not recognize any other self antigen. If you have those other self antigens, you're not supposed to recognize them, because if you did recognize those self antigens, what's going to happen? You're going to be inducing an immune response against your own cells, attacking your own cells and destroying your tissues. And this is going to result in autoimmune diseases. Of course, you hear a lot about autoimmune. Auto means self. I'm creating an immune response against myself. I'm attacking my own tissues. So what those cells need to do, they need first to learn how to recognize a self-antigen. We call the self-antigen on here, it's my MHC, major histocompatible protein. If you did pass this class, you're going to pass through another selection process to test your ability, whether or not you are not recognizing any other self-antigen. So again, I have two steps, two selection processes that I need to pass through as a B or T lymphocyte. in school. I didn't graduate yet. I'm still learning how I will be recognizing the antigen. So first thing I did learn in school to recognize one specific non-self antigen. I will only recognize an antigen on rubella. I'm only gonna recognize an antigen on measles, only on mumps, only on streptococcus, and so on. So I'm able to recognize again a specific non-self antigen. But I need to make sure that those graduating cells will not kill me. All right. So I need to make sure that they are capable to recognize the self antigen on which you're going to be presenting other antigens that might be non-self. And we call those antigens which are selves. This is self antigen. I need to recognize it. I need to be able to bind to it. It's called MHC, major histocompatible protein. This is a self antigen, but you need to recognize it. If you were able to recognize the MHC, you're gonna graduate from this class and pass to the second half of the class, which will be testing your ability to not recognize any other self antigens other than MHC. Is this clear? Clear? All right, so what do we call the first selection process? We call it the positive selection. What I mean here, I need something to be done. I need to be positive. I need to do something. What is the things that I'm trying to do on here? I'm trying to recognize. I'm trying to recognize MHC. What if I failed to recognize? Can I repeat this course? No, you're gonna be destroyed. All right, so if the cell did not recognize MHC, I will attack it and induce apoptosis. It's gonna be destroyed. How about the cells that were able to recognize the MHC? Now they are graduating for the next course, so they will be passing through another selection process, and this is gonna be requiring them to not recognize self-antigens. That's why we call it negative. I want you to not do something. So it's a negative selection. I will select those who will not recognize. It's negative. Here, I'm selecting those who will recognize the MHC. It's a positive selection. So we have two selection processes that the B and T lymphocytes is going to be passing through in order for them to become self-tolerant, I make them graduate from either the thymus gland or the B is a bone marrow. All right, so again, here, in order for me to become self-tolerant, I'm passing through two selection processes. First one is gonna be the positive selection. And in the positive selection, I will be recognizing a self-antigen, which is MHC. If I failed to recognize MHC, cells gonna be destroyed. What if the cell was capable here to recognize the MHC? You're good. you're going to proceed to the next step. You're going to be passing through a negative selection process. All right, T lymphocytes going to be in need to not recognize self-antigen. While we're focusing here on the T cells, this is something that we're going to get back to when we discuss details on how the T lymphocytes are going to be responding. All right, so again, what is the story here? Start by forming the lymphocytes in the red bone marrow. They need to get their education. They get their education for the B lymphocytes in the red bone marrow, and for the T lymphocytes, they need to travel outside of the bone marrow to the thymus gland. Now, those cells are called immunocompetent cells. When they graduate. But in order for them to graduate, I need to make sure that they won't attack me. I need to make sure that they have self-tolerance and they are able to recognize and bind to their specific antigen. So I need to bind to a specific antigen and I need to be self-tolerant. Again, how would I be self-tolerant? Here we're focusing on the T cells. T cells will need to recognize the self-antigen MHC. If I fail to recognize MHC, the cell gonna be destroyed. If I did recognize MHC, I'm good to move on to the next step, which I get exposed to this different self-antigen. If the cell binds tightly to the self-antigens, this means it's recognizing the self-antigens and is going to cause a problem later on if it did graduate. It has high affinity to the self-antigens. So if I found cells which are getting attached to the self-antigens, it's now time to get rid of them before they start to attack my own tissues later on. So I get rid of the ones that will fail to not recognize they fail to not recognize the self-antigen. For those who want to recognize the self-antigen, they will be good to leave school. Now they are graduating, and what do we call those graduated cells? We call them immunocompetent cells. What is everybody looking forward to do after graduation? Why do we go to school in the first place? What do you think? Job, work, exactly. To pay for vacation. Because we need to work first to get the money to pay for the vacation. So still, we're gonna have to go to work first. All right, so going to vacation, but before that, we need to find a job. All right, so what are my chances as a fresh graduate of getting a job? Not too high, not too high, low, internship. So you are realistic. You're good. You're good. You're good. Yeah, very little chance to find a major position when you just graduate. You need to look for a place to get trained, right? So here, those are immunocompetent cells. they did receive their education. They've learned, they graduated, but they don't have any experience. We call those cells are naive cells. They are still naive. They don't have experience. So they need to get some kind of training, so an internship. So where would I get the internship as a B or T lymphocyte? I will go to the lymphoid organs. And that's why those cells are called lymphocytes, because when they first got discovered, they were not discovered in the bone marrow or the thymus gland. They got discovered in the lymphoid tissues, lymphoid organs, lymph nodes, spleen. So this is where they will get their training now. This is where they face real life. This is where they will encounter the pathogen for the first time. Yes, they've learned how to recognize it. They've learned to become self-tolerant, to not attack my cells, to recognize MHC. Everything is fine with me. I've got the education needed to do the work, but I don't have experience yet. I've never got exposed to a real pathogen before. So where would I meet the pathogens that I have learned to detect and recognize? In my lymphoid organs. Once you get the exposure to the specific antigens that you are supposed to recognize and you become activated, at this point, you got the experience and now you are activated, and those activated cells are the ones that will do the job. All right, so the first encounter between the antigen, which is the non-self antigens that I am gonna be recognizing as a B or a T lymphocyte, this first encounter takes place in lymphoid organs, lymph nodes, spleen. All right, those activated cells are the ones that will be attacking, those ones that will remain semi-activated, silent as memory cells. So whenever you get re-exposed to the same antigen again, you start the attack at a very early time, as we can see after. Any question? Any questions so far? We're going to be discussing after we come back from the break how the B lymphocytes, the T lymphocytes are going to be acting in order for them to attack the pathogens. But before we leave to the break, any questions? Any questions? Anybody is still here? All right. Update for the lab exam. So I did check out the ones that you told me about last class, and it needs an institutional subscription. I'm not sure how the other professor was able to get you taking the test over their platform. But I've been speaking to the Proctor representative, and what she told me, yes, as you told me last time on Tuesday, that yes, they will be charging $25 per exam for a 2 hours exam. All right, so we did have a meeting with the president of the college yesterday with other departments and all representatives. I did address the question of whether the college is moving forward to have an institutional subscription for one of those online proctoring platforms. And they are still looking at the budget. They are not sure whether they will be able to do it or not, but I know for sure that somebody is negotiating with multiple platforms. So I will keep it on hold for now until I hear back from them if they will be doing anything about it or not. And if not, I have the test ready on ProctorU already. So I don't wanna I don't want to open the window for you to take it on ProctorU until I make sure that the college won't be uh, uh, sponsoring the they won't be sponsoring the proctored examination platforms. All right, so until then, we're still on hold, and I will be getting in contact with them another time on Monday, and we'll see what they they've reached. It seems that they still have some hope to move back to campus. For lecture exam is going to be the same structure, the same way that we are addressing the quizzes, the chapter quizzes. It's going to be on Canvas. It's not proctored, right? But for the lab exams are the only ones that will be proctored. So we still have 3 more labs and an optional final. So a total of 4 exams that will be proctored. I want just to wait until I hear back from the college whether they will reach an agreement sometime soon or not. Lecture exam is on Canvas. You can complete it. I believe it's open already, or it's going to open in a day or so. And you have over this weekend to get it completed for the Tuesday, Thursday class. And for the Wednesday class, your the due date for the lecture exam was yesterday. For the disruptions we've had, I will be adding an extra exam, extra quizzes at the end of the semesters that will be substituting any exams that you were not able to attend or you were not able to complete, or you didn't score well on it because you didn't have enough time to prepare. So anything like this will be substituted. So one exam is going to be substituted, 2 quizzes going to be substituted towards the end of the semester by the additional exams and quizzes I will be posting. But don't plan to miss an exam intentionally because you have because you know already that you're going to be having those extra quizzes and exam towards the end. So don't plan it ahead. So you never know what's going to happen. All right. Sometimes you're going to totally forget about the due date or something happens with you. So now we have many interruptions in the internet connections that I'm personally experiencing. So it seems it's going to be more challenging to have a stable internet connection with everything moved online. So hopefully everything goes fine. It's good so far with the wired connections I've done. but we can have a break now for 10. I will keep the timer. So, all right, so we're gonna have a break for 10, and we're gonna come back, complete our discussion of the adaptive immunity.